All right, grade 11s. So this is the third lesson in our finance unit, our last unit. This one is again looking at compound interest, but this time we're going to be determining the present value of an investment. Um, so in other words, that means figuring out the amount of principal needed in order to have a given amount in the future. So the idea here is like we have a goal in mind or an amount of money that we need a year from now or 5 years from now, and we're trying to kind of plan for that and invest the right amount at the beginning. So we have our note, a little bit of textbook practice, and then this afternoon, as I've mentioned a couple times, we're going to have an open book assessment. Okay, so these questions are going to be asking how much money is needed now in order to have X dollars in the future or some amount in the future. Really, this could say A dollars in the future. Um, but that means the goal for these questions is going to be solving for P. That's not what the compound interest equation is set up for. This has A, like the final amount by itself. So if we're trying to solve for P, we're going to have to do a little bit of rearranging. All right, so I'm going to set that up. It's a really quick bit of algebra to isolate the variable properly. If we're trying to solve for principal, that means we need to get rid of this whole power. If we want p by itself, we have to get rid of that power. So we're going to divide by that whole power and do the same to the other side to keep the equation balanced. On the right-hand side, we have something being divided by itself that always reduces to 1 over 1 and kind of disappears for us, which is the point. And then we're left with only p on that side of the equation and all the interesting stuff on the other side. So I'm just going to flip the two left and right hand sides so that p is showing up first. That's my preference, but if it doesn't bother you to have your variable on the right, you can leave it alone. Um, 1 plus I to the exponent n. Okay, so here's our rearranged version of the compound interest formula. This one's set up to help us find the principal amount of money. If we know the final amount, the number of compounding periods, and the interest rate. Alrighty, so we're going to look at two problems. This is compound interest, so I've highlighted some of this stuff, and we're going to pay attention to how the money is being compounded. So whether that's annually or on some different schedule. So here we have Jackson, whose parents want to have $15,000 saved for post-secondary education when he turns 18. And they decide on depositing money at birth into an RESP, which is a registered education savings plan. So they decide to deposit money when he's born that will earn 8.5% interest compounded annually. After that initial deposit when he is born, there is no more deposits until he turns 18. Okay, so it's just like a one-time lump sum investment that they're trying to decide on how much money do they have to put in. So the variables that we are going to be using. Principal, we don't know it. It's not given in the question. That's our goal. The final amount of money, that's our goal. That's $15,000. The number of compounding periods, this is compounded annually. So once per year for 18 years. That's just 18 compounding periods. And the interest rate is going to be 0.085 in decimal form. If you want to say you can like divide by 1 because it was annual, but that doesn't really do anything. All right, so there are our variables. The formula that we came up with on the last slide looks like this. We can substitute our known values into the formula. So P equals 15,000 divided by 1.085. So when I do that substitution step, I actually add the 0.085 right to the number 1. I don't write that as two separate steps. That seems like it shouldn't really be necessary. And then punching this into a calculator, 15,000 divided by 1.085 raised to the exponent 18 should help tell you $3,454.27. So that might be surprising. If Jackson's parents invest just like $3,500 when he's born, that will be $15,000 by the time he's 18, ready to head off to school. So that is like the benefit of compound interest. The earlier you start saving, the bigger your money will grow to in like a reasonable amount of time. So 18 years. This is a pretty high interest rate, 8.5%. I don't know if that's typical of investments or if that's on the high side, but that sounds pretty great to me. $3,500 today, $15,000 18 years from now, I can handle that. In theory, at least. So how much money should be invested today? If you wanted to do a therefore statement, you could say, therefore, Jackson's parents need to invest or deposit, you can use whatever word you like, $3,454.27 when he is born. If you're wondering how that works, or like what some different scenarios could be, maybe a family decides when their child is 5 years old, oh, we probably should have started in our RESP. That means they still want to plan for like a future education cost, but they're not going to have 18 years to grow their money in the bank. So if you started at 5 years old, you'd have 13 years for the money to grow. You would need a bigger principal amount to make that happen. So you can kind of play with that and say, what happens if the exponent was 13? What if we didn't start saving until the kid was 8 or 10 or 12? So you're just shortening up how many compounding periods there are, and that is going to require a bigger and bigger principal. All right, example number 2. This one is about Max. This is kind of the opposite situation. Instead of planning for a future goal amount of money, we have Max borrowing money from his parents. So taking out a loan today. He borrows money from his parents to buy a used car. In 6 months, he owes them $2,500, including interest. I should have highlighted that too. So he's going to be paying them back $2,500 in total. And they charged him an interest rate of 18%, compounded monthly for that time. How much did he pay for the car? So when he first bought it, what was the cost? How much did he borrow from them? Okay, so in this question, the final amount of money that he's going to be paying back is $2,500. Part of that is the principal that he borrowed. Part of that will be interest that has been added on top. The principal is unknown. The number of compounding periods, this is compounded monthly for 6 months. So monthly for 6 months. 6 compounding periods. And for the interest rate, 18% written as a decimal, but that's actually going to be split into monthly chunks. So we'll divide it by 12. that becomes 0.015 or 1.5% each month. Okay, so there's all the information we're going to need. We can set up the equation one more time. And I'm actually going to solve this one in two slightly different ways just to show you an alternative that you might like better. So I'll do the first one the same as our last example, and then I'll rewrite it slightly differently. Oh, I forgot to plug in the known amount in the numerator. It was $2,500. Okay, if we punch that in the calculator, 2,500 divided by 1.015 raised to the exponent 6, the answer I'm getting is $2,286.36. Okay, so that is how much he paid for the car originally. So he borrowed exactly this amount of money to pay for the car. Um, his parents charged him interest on top of that. So after 6 months, he actually had to pay back a little bit more money. He had to pay back 2,500. So there's 220-ish dollars of interest he owed them. If you're curious how much, we could actually subtract the final amount minus the principal to see how much interest his parents charged him. So I'll do that just quickly out of curiosity. 2,500 take away 2286.36, and that is $213.64. So his parents weren't messing around. They said, yeah, you can borrow the money, but you're going to be paying us interest. And that's not a small amount. Okay, so I said I would do this one in two different ways. And that's going to be a twist on like the original formula. So I'm just going to stretch this page out and show you kind of method number 2. So that original formula that we've been using in these two examples was original amount of money divided by 1 plus the interest rate to the exponent n. And that involves like using a fraction, which some people are scared off by. So we have some exponent rules that we used before the break that we could make use of here. A fraction that has a positive exponent, we can change that by using a negative exponent. So if I want to move the bottom to the top, the denominator to the numerator, I'm going to have to change the sign of the exponent. Okay, so that's going to become 1 plus I to the exponent negative n. So a little bit weird, but we did do these exponent laws with the negative exponents. If we saw a negative exponent, we could take the reciprocal of that, which pushed it into the denominator. So we're kind of undoing that and giving this a negative exponent now. So I'm going to show you what that looks like for this question. The final amount of money was 2,500. The interest rate was 1.015 raised to the exponent negative 6. That's a little bit nicer to type in a calculator. It's a little bit nicer to write on your page instead of fractions. And to type this in a calculator, I would say 2,500 multiplied by 1.015 raised to the exponent negative 6. And it does give the same answer. You can try both of them and see which setup you prefer. Both of them are totally fine. So therefore Max paid $2286.36 for his car. All right, so that's it for compound interest. The first video covered questions where you knew how much you were starting with and you wanted to know how much it could grow to. And here we are thinking about an end goal and trying to work backwards to figure out the initial investment. All right, the homework here is again from the textbook, page 365 this time. And these questions are listed in the heading for today in the content. All right, so that list shows up there as well. If you have any questions, join me in the help session. Yeah, and you can look at the schedule to find out what time that starts.